Another use of differentiation is to find extreme values in functions. Where do they reach local maximums or minimums? And other critical points, such as where are they changing in their rates of change from up to down? We're going to use differentiation to find those. So let's give some definition to that word extrema. So if we look at any interval that contains an x value that we'll call c, the function is called being a minimum if the value of the function is less than all the other values of the function on that interval. It's a maximum if the value of the function is greater than all of the other values of the functions on the interval. And we call these minima and maxima the extreme values, or the extrema, over the interval. So let's take a look at what's called the Extreme Value Theorem. Now, the Extreme Value Theorem says that if a function is continuous on a closed interval from a to b, then the function must have both a minimum and a maximum on the interval. Let's look at the Extreme Value Theorem kind of intuitively, not formally prove it, we're going to look at it intuitively. What it says is that if I've got a closed interval from a to b, and the function's continuous, and those things are important, then it must have a minimum and a maximum on that interval. So I'll draw a function, just any kind of random function, and it can continue beyond the boundaries, but we're concerned about what's happening on the interval. On the interval, between a and b, it's got to have at least one minimum and maximum. And I would challenge you to draw any function that wouldn't have at least one, and probably more, minimums and maximums. The one possible thing to look at would be a horizontal line. Okay, it's continuous, it's between a and b, but there is no minimum or maximum. But in this case, the value that it constantly is the minimum and the maximum. So let's apply the Extreme Value Theorem to find the extreme values on these functions. We'll look at the function f of x equals x squared minus 4x plus 5 over the interval from -1 to 3, the closed interval. So we're going to look at the interval of this function from -1 to 3. And the Extreme Value Theorem says that since the function is continuous from -1 to 3, and in fact it's continuous through all real numbers, there must be a minimum and a maximum over that interval. And in fact, you can visually see there's a minimum at x equals 2, and there's what we would call a local maximum at x equals -1, y equals 10. This visually kind of shows you how it works, but let's start to look at what's happening at those minimums and maximum. So the minimums down here, what do you notice about the derivative or the slope of the tangent line at x equals 2? And I've just drawn the tangent line there through GeoGebra, and you can see that it is horizontal. So this is an absolute minimum for the entire. Now let's look at a cubic function, f of x equals x to the third minus 2x squared minus 3x minus 2, and we're going to look over to the same interval from -1 to 3. Now visually, you can see that there is a local maximum and a local minimum on this function, and both of them, at both those points, it looks like it's somewhere between 0 and -1 in the x, and somewhere slightly before 2 for the other one. At both these maximums and minimums, the slope is going to be 0. Visually, visually now, you can see I've drawn the tangent lines here at this point A and this point B. Visually, you can see the slope is 0 at that point. Local maximum at point A over the interval, local minimum at point B, and this is over the continuous interval from -1 to 3. Okay, so I used some terminology and I need to clarify it. Over an interval, the extreme values are called relative maximums or minimums when we're talking about an interval. So we're going to use that term relative to mean over an interval because the function could do something else outside the interval. Any open intervals containing a maximum value are relative maximums. Any open intervals containing a minimum value are relative minimums, again, over that interval. But we're going to also use this term absolute maximum or minimum to denote an absolute maximum value or minimum value over the entire domain of the function. So we can have relative maximums or minimums that may not be over the entire function, but over a certain interval they are. But absolute absolutely is over the entire interval. So let's look at the function f of x equals 9 times the quantity x squared minus 3 divided by x to the third. And here's a graph of it. And you can see visually it looks like we've got local minima over here near -3 and a local maxima at 3, at x equals 3. If we have, say we define an interval from -4 to +4, if that's our interval, then we have a relative minima at x equals -3 and a relative maxima at x equals 3. Now that doesn't mean they're the absolute minima or maxima. You can look at this function and see the absolute maxima is really positive infinity. The absolute minima is way down below at -infinity. And you can visually see, you can graphically see that the slope of the tangent line at that minimum, at that relative minimum at point B, and that relative maximum, point A, is 0. Now let's look at the function f of x equals the absolute value of x. Let's look over the interval from -5 to x equals +5. So we're going to look over this interval right here. Visually, we're going to look and see over the interval, it's going to have relative maximums at x equals -5 and x equals 5, the endpoints of the interval. It has a relative minimum at x equals 0, which happens to also be the absolute minimum of the entire function. What about the slope? Well, the slope at that absolute minimum doesn't exist, because if x is greater than 0, the slope is +1. If x is negative, if x is less than 0, the slope is -1. So in this case, the function does not have a slope, it does not have a derivative at x equals 0 because the limits are two different limits. All of this leads to the idea that relative extrema occur at either points where the derivative is 0 or does not exist. And the x values of these special points are called critical numbers, points where the derivative is 0 or does not exist. So here's kind of the big definition of critical numbers. If the function is 0, or if the function is not differentiable, in other words, the derivative does not exist at that point, then C must be a critical number. And that's where relative extrema exists. And relative extrema will only occur at critical numbers or at the endpoints of intervals. So a process for finding extrema. First, find the critical numbers by setting the derivative equal to 0. Also, look for places where the derivative fails to exist. Then evaluate the function, not the derivative, the function at each critical number and the endpoints, because again, on an extrema can exist on endpoints. The smallest value is the minimum, the largest value is the maximum. So let's do an example. We'll look at the function f of x equals 4x divided by x squared plus 1 over the interval from -4 to +4. So if we use the quotient rule on this function, 4x is the numerator, x squared plus 1 is the denominator, we get low d high minus high d low over the square of what's below. So we're going to simplify it, and it simplifies down to this, 4x squared plus 4 minus 8x squared, which in turn is 4 minus 4x squared, all over x squared plus 1, the quantity squared. And what we're going to do is we're going to set that equal to 0 and find out where the function this derivative function either doesn't exist or is equal to 0. So to do that, all we have to do for a rational function is find out where the denominator is 0, because that's where it's not going to exist. That doesn't happen here. X squared plus 1 will never be 0. So now we're going to focus on where the numerator makes the entire function 0. So since there is no place where the derivative fails to exist, because the denominator is not equal to 0, we're going to set the numerator equal to 0, which is 4 minus 4x squared equals 0. That leads to two solutions, x equals plus 1 and x equals minus 1. These are both critical numbers. So if we evaluate the function at these two critical numbers, not the derivative, but the function, we already know the value of the derivative is 0 at these points. The function has a value at -1 of -4 over 2 or -2. The function at 1 has a value of 4 over 2 or 2. We know that f of -1 is going to be the relative minima of the function. F of 1 is going to be the relative maxima, because relative minima and maxima must occur at critical numbers where the derivative is 0, as it is in this case, or fails to exist. Let's see if the graph of the function bears this out. And it does. At x equals 1 and x equals -1, the function has relative minima and maxima, because these are critical numbers. In fact, these wind up being the absolute minima and maxima of the function. So let's examine the function f of x equals 2x minus 3x to the 2/3 power over the interval -1 to 3. So don't forget to evaluate the endpoints as well. So we take the derivative, f prime of x, and that's going to be 2 minus 2x to the minus 1/3 power using the power rule. We're going to set that to equal to 0 because extrema can only occur at critical numbers, and critical numbers occur where the derivative is equal to 0 or does not exist. If we factor that, we get 2 times 1 minus 1 over the x to the 1/3 power. So critical numbers occur at two places. First of all, where x equals 1. At x equals 1, or the derivative is 0. Also, at x equals 0, the function of the derivative fails to exist. Therefore, x equals 1 and x equals 0, critical number. So what I'm going to do here is make a table. First of all, I'm going to put the endpoints at the end of the table with the x values in the first row and the f of x values in the second row. So we know the extrema could possibly occur at the endpoints or at the critical numbers that we determined, 0 and 1. So we're going to evaluate the function at all 4 points. So when we find the values of the function at those 4 points, both the endpoints and the critical numbers, we find that the relative maximum occurs at 0. We find that the relative minimum occurs at x equals 1, where the function has a value of -5. We know that extrema can only occur where the derivative is equal to 0 or does not exist, or it could possibly occur at the endpoints if we have a defined interval. So the process in finding extrema, once again, first of all, find the critical numbers where the derivative is 0 fails to exist. Secondly, evaluate the function at each critical number and at the endpoints. And the smallest value is going to be the minimum, the largest is the maximum. Extrema and critical numbers. Critical numbers exist where the derivative is equal to 0 or the derivative does not exist. Extrema can only occur at these critical numbers or at the endpoints of an interval.